no problem at all.
Excellent. Okay, so let me talk about really the whole paradigm shift. And I was going to say, is it real or isn't it? But no one is going to say that it's not real. It really is obvious. It's going to happen, and it's going to be enormous. I think, if anything, people in the industry are understating what the shift is going to be like. It's a good synopsis of the course anyway. So I'll go over the fundamental mysteries, and I think you're very comfortable with them, aren't you?
Yeah, I think so. I think so.
Yeah. So I'll be going through those rather quickly. If anything, I think, although I've enjoyed all the sessions, to be honest, but I thought the first session with Bodhi, now Bodhi has been to my quantum consciousness presentation, so he's on the spiritual side, but I thought that was a wonderful, we really got down to some good stuff. So
it was engaging. That's right. I mean, it asks questions that that there aren't really any clear answers to, and it will probably be kind of one of the consciousness. I think maybe questions that will need to fall, to make this truly, I guess, transferable.
Yes,
as in information transfer.
Yes, I honestly believe that within 100 years, and hopefully sooner, but we will understand the collapse of the wave function. And should that solution be consciousness, then wow, it beggars belief where we'll go from there. It'll be a very exciting time.
Yeah.
And so I'll talk about the commercial applications of quantum computing, and then I'll talk about the comparison. And we've done basically sessions on both of those. So we obviously won't be going down to the computation level, the way we manipulated around the block sphere, which was a fantastic journey, as it always is. But again, I'll be touching on the comparison of quantum computing technologies. And I think that's going to just become bigger and bigger, because someone is going to make a bit of a leap forward. And it'll be interesting who does that. And then there'll be the 8-minute video on Qiskit that is always good to see. It just shows how easy it is. Are you a member of, I'm sure you are, of IBMQ experience?
Yes, I am. Yeah.
Yeah. But still, it will, it'll be good stuff. So I might just put the video panel on. I like having that there. Okay, so the fundamental mysteries of quantum physics, which gives us the wonderful forces of superposition, quantum entanglements, and quantum tunneling, which we still don't understand, but we can use complex mathematics, linear algebra to reference and to use. The double slit, originally brought in to see whether light was a wave or a particle. It proved that it was, proved in inverted commas, that it was a wave, because that's all the professor, oh my God, I've forgotten his name now. I should, Professor Young, that's all. Professor Young just, didn't collapse the wave function. So he mistakenly, which shows how science has to be careful, but he mistakenly thought that it was proof it was a wave. Einstein came up in 1912 with one of his 4 pivotal papers on the photoelectric effect, which proved it was a particle. So it was just amazing. And the thing is, as we all know, the particle is in a superposition until it's measured. It's in a wave function that we have managed to quantify by linear algebra in the Schrodinger equation. So the Schrodinger equation shows you the movement of the wave through time, and then with the Born rule, at any part of the wave, you can work out the probability that the particle is there by squaring the complex amplitude of alpha and beta, of 1 and 0. So you can work out the probability that it's 1 or the probability that it's 0. And that's just an amazing part of quantum physics that we can utilize, even though we don't fully understand. So when the camera is there, the backboard changes into the clump pattern, so it's behaving like a particle. Quantum entanglement, which is how we got to the session on quantum teleportation. Entanglements, like in the Bell state, is where the subatomic particles have this, they both depend on each other, they're non-local, there is some connection between them that we don't fully understand. And Einstein called it action at a distance. Yet with the quantum teleportation, the Chinese managed to completely reproduce and re-engineer the exact same subatomic particle from the laboratories in China to an orbiting space probe called Messias. And it worked fine, and they've done it thousands of times since then. And I think, as I said at the session, isn't it amazing that we can do that wonderful thing so easily by merely using a few gates, and we can do conceptually. The practicalities, of course, are difficult, but for a quantum theorist to work out what needs to be done to teleport a thing is incredibly easy. Quantum tunneling is the reason why Moore's law's finished with, because we actually can't get any smaller now than the current sizes of the chips on the integrated circuit, because they're now beginning to obey the laws of quantum physics rather than the laws of Newtonian or classical physics. And we're shooting voltage through there, and unfortunately the subatomic particles are able to walk through the walls, basically. It's a very interesting phenomena, and possibly doesn't get the attention that the other two can or do. Quantum tunneling is thought to be very important in quantum biology, where some of the things we've never understood, like bird migration, or by our own brain functioning, how it happens, the messages don't really go from synapse to synapse as we thought. There's an awful lot of quantum tunneling. It's a great area which I'm reading up and thoroughly enjoying, but neuroscience is big on. Quantum tunneling is coming to, is explaining some of these incredible features. Yeah, I then spoke about the reality or the connection between quantum computing and quantum physics. So the amazing way that we have the qubit collapses to 0 or 1, and that is what happens when we collapse the wave function. So all that's happening on the qubit, which could be an electron, it could be a photon, it could be light, it could be the movement of electrons in a superconductive situation where the energy is quantized through a Josephson junction. And it's the same thing that's happening. Born's rule is the probability of the wave function collapsing is equal to the absolute value of the complex amplitude squared. And again, so that's something that is regularly used. The fact that a squared plus alpha squared plus beta squared equals 1. And that's just, again, and it allows us to pinpoint any part of the wave function and the probability of the particle being there or ending up there, collapsing to there, is the square of the amplitude. And this is the most important equation in quantum physics and quantum computing. Psi is the wave function, and the probability of it being 0, so we've got the ket, so the probability of it being ket 0 is alpha, and the probability that it goes to 1 is beta. And that's how they all start. And then by applying gates, we can put them into superposition, which changes everything. It then becomes 1 over square root 2 for each of them. So, yeah, it's amazing. The Born equation, as I mentioned before, alpha squared plus beta squared equals 1. And then the fact that we're looking at surface locations on the Bloch sphere, that's just, Bloch sphere notation. And the no cloning theorem, which is a physical law, is we cannot know, it's back to the uncertainty principle, is an extension of the uncertainty principle from Werner Heisenberg, where we're just simply not allowed to clone a wave function. So if we have a wave function that has a certain alpha, a certain beta, we cannot clone it. We cannot take that, copy it, and put it somewhere else. When we actually teleport it, it must collapse first. We cannot have it cloned, which is good and bad. It's I always joke with people that it's amazing a quantum computer can't copy and paste. Well, that's why. And then when we talk about the exponential speed of the fantastic increases we're going to get in certain circumstances, 10 to the 28th, which is a million, comes down to the difference between 1 and 0, and then everywhere on the Bloch sphere, which can be referred to. And then there's the trigonometric equation, which basically just allows us to move incrementally around the 3 spheres, the X, Y, and Z. God, I'm sounding American now. The X, Y, and Z spheres, hemispheres. So it's it gives us so many more possibilities. And then when you entangle them, the important thing is when we entangle qubits, we're exponentially increasing all of the mappable spaces that we have, and we're working in a larger space. So the important thing is that quantum computers are, the algorithms that we're going to be able to write. There's 2 things to be aware of at the moment with algorithms and the technology that we have. We have NISQ technology, noisy intermediate scale quantum computing, and FT computing, which is fault tolerance quantum computing. So that's pure versus the very noisy that we all have. We all know about decoherence how the electron or photon, whichever one the technology is, in order to gang up with other qubits. We wanted to do that, but there again, we don't want it to interact with the environment, which it does very quickly and then kills everything. All the algorithms we have at the moment running on NISC are heuristic. And heuristic, H-E-U-R-I-S-T-S-C, means that there probably is a speed up advantage, but we don't know for sure. Whereas with the likes of Shaw's, Grover's, all the really big algorithms will only run on a FT quantum computer. So, you know, running Shaw's on NISC just is a pointless exercise because it decoheres so quickly, it doesn't get to the answer, the solution. QML and QAI are obviously two very, very big areas, as is 100% data security, which is quantum key distribution. So by it's setting up a cloud infrastructure that we currently have at the University of Delft in Holland, which I keep in touch with. And proving that it's 100% secure. So I'm not sure how they're going with that, but again, in theory, it shouldn't be a problem. And then quantum teleportation, as the session that we had, is just a fantastic area where we've unbelievably been able to teleport an atom, a subatomic particle. We've broken it down and taken the code and then re-engineered that code onto a subatomic particle 1,500 kilometers away. And that, when you think about where that's going to go, it's amazing. So the commercial applications, as we mentioned before, the finance industry is obviously huge. Quantum chemistry is what Feynman originally invented, let's call it, quantum computing for. He said the only way to do what happens in nature is with a quantum computer itself. And that's led to things like sequencing the genome. My friend Cohen Bertels in Spain now, he's moved from the University of Delft to Spain, and he's doing some great work with a company called QB on sequencing the genome in the quantum realm. That will lead to personalized medicine and vaccines, protein folding and EV batteries modeling, being able to model nitrogen. 2 or 3% of the total energy on the planet goes towards the production of nitrogen. Even though bacteria do this automatically, we cannot figure out with our current digital computers, we can't simulate nitrogen conversion into fertilizer. So quantum simulation of the Big Bang, weather, all of those things, simulation and optimization are really big applications. And then we have optimization, we have automated traffic, so a real e-vehicle network, and freight, which is the optimization, which is very poorly done at the moment. So if you're aware of the knapsack problem, it's actually a solution to the knapsack problem. and again could make the whole world far more efficient. So the comparisons of the technology, which I found a very interesting session here. So I've compared 4 here, which are the superconducting loops, trapped ions, topological qubits, and photonics. So here we've got the likes of Google, IBM, Oxford Quantum Circuits. And for the trapped ions, we have Honeywell and IonQ. And topological qubits is Microsoft and Bell Labs. So, these people aren't fools. They're all gambling, if you want to use that word, on the technology. And then we have photonics, the likes of Xanadu. And I noticed that the recent National Quantum Showcase in the UK, there were lots of photonic companies. So they're coming out of everywhere. It's very interesting. So we have different numbers of qubits. So we have, in the superconducting world, IBM are talking about 1,000 qubit system in 3 or 4 years, or 2 or 3 years. Things always happen sooner in this industry than we anticipate. Honeywell are talking about, never mind Moore's law, which is doubling every 18 months. Honeywell have predicted moving at 10 times every year. And in the photonic world, I might add, Xanadu are talking about increases of tenfold for every 8 months for the next foreseeable future. And there's some interesting technical reasons why photonics will be able to move through the NISQ era and make most use out of the NISQ era, but will be a technology that will be feasible in the FT quantum world. And then the topological qubit on the incredible Majorana fermion, which is a particle that is its own antiparticle. So that's an amazing technology, and Microsoft and Bell Labs predict that it will, in the medium term, it will, absolutely leapfrog everything else by a multiple factor in such a way that every single software developer would have to migrate to a topological qubit. I might add that whereas superconducting qubits are talking in the thousands, topological qubits are still sub 10. So we can see how you can't compare technologies by the number of qubits. And then you've got your room temperature, quantum microprocessors, like the NVC, the nitrogen vacancy centered of diamond technology, which has been around for 20 odd years. So it's all exceptionally interesting. What I'll do now is just show the video. Okay, so here we go. I'm going to start at Google so we all know where we are. Type in IBM Q Experience, and then you go great to the page. Heaps of stuff on here explaining tutorials, explaining what everything is, FAQs and everything. I'm just going to log in because I've got a username and password. But if you want to join, you just join, give them a username and password. It's all free. On the left-hand side of the menu bars, and I'm going to go here, which is the Circuit Composer. And you see these ruled lines here, like ruled lines on the paper. like in musical notation, they are actual registers for qubits. So there's qubit 0, qubit 1, qubit 2, and then there's a classical register, so that when you measure it, you can download it to a 1 or a 0, and you know the qubit, the quantum processing has been done. Notice I've got views here like the Q sphere and the measurement probabilities. They'll keep telling me the ramifications of everything I do. Now I could use code if I so wish, but here I'm going to use the palette of gates just to show you how easy it is. I'm going to use the principles that we've just learned, like superpositioning and entanglement. I'm going to do a quick quantum programming for entanglement, which is in almost every single quantum algorithm. I'm going to drag down the Hadamard on the first qubit, and I'm going to do a control gate on the first and second qubit, and then I'm going to measure these. Now, what happens is the Hadamard gate puts it into superposition. A Hadamard gate in conjunction with a CNOT gate, a control NOT gate, gives you a superposition. And I can tell I'm in superposition because with the measurement probabilities, I've got a 50% chance of being 1 or 0. And that's showing me the state here. Probability that it's 0, probability that it's 1. I'm going to call this aim and simulation because I'm going to put it on a simulator. So now I'm going to look at my run settings, and here I can send it to any quantum computer I wish, IBM quantum computer. They've got 36 now, and they're increasing all of the time. And you can see how big they are. Melbourne's a 15 qubit, and then the others are 5 qubits, and you know they're getting bigger and bigger. To begin with, I'm going to do the simulator, and that's going to run in seconds. And what I'm going to do is run the simulator. The job's now been sent, so I can check on the job. It's been sent, it's running, and of course it's completed exceptionally quickly because it's only a simulation. So if I go here to the left-hand menu, I can look at my jobs, and I can see I've got one here completed a few seconds ago. I can open it up. It's now transpiling, validating, and here's a histogram of the result. I can download it. I can do all sorts of things. And you can see it's nearly 50%. And that's because I think I ran it 1,000 times. You get the choice of running it so many different times. So that was lovely and easy, wasn't it? I can now go and do the same thing again for an entangled state. And this time, and you can see that last time I'd forgotten, I just ran it 1,024 times. Now I'm going to choose, and I can look at how many jobs are around and how long I'll have to wait at any one of them. But because I'm recording this, I'm going to put it on pause anyway. But I'm going to go to Melbourne, and I'm going to run it on the quantum computer in Melbourne. It's now been sent, and it's now queued. Oh, that's not too bad actually. So it's going to run in 7 minutes. If you pay IBM, like for instance Woodside here have locally, you can access a quantum computer immediately. But every single person or small business in the world can do what I'm doing and access it for free. You just have to wait a few minutes. 6 minutes is quite good. I'm going to pause the video and resume once it's about to finish the when it's going to run the job. Okay, I'm coming back live here now, and you can see that there's around about a minute to go, and that we're still queued. I did forget to name it, but I can do that at any stage. So I'll say QC because it went to a real computer rather than just a simulation. I might show you a menu item here while it's still coming down, which is inspect. It allows you to, just by clicking on each of the items, you can go from one to the other, and look at the change it's making here to the visualizations. So that's it in its Hadamard state. And again, you just click from one to the other. It's actually, it is really very, very useful so that you know exactly where it is. Oh my God, it's gone up to 3 minutes. I'll have to pause you again. That obviously happens like in anything. I'll just pause you and be back in a minute. Okay, well, it's now completed. So you can see the back end, the IBM Q16 in Melbourne. And there's the provider. It was finished on August the 20th. Completed. So I can now view it. And here it is here. So I've got 2 items. The other one I did. So I'll open it up. And here we can see, do you remember, for the perspicacious of you there, when I did a simulation, it was either all zeros or ones, and that's because it was simulation. Notice here, there are some, this is basically decoherence, noise. The whole problem with getting quantum computers off the ground now is that it interacts so delicately with the environment. The slightest bit of radiation and data is lost. That's why half the qubits are performing fault tolerance on the other qubits. But here we can see a little bit of noise, and I must admit I've noticed that those percentages have been going down. So we've now seen how we can quickly do a program, a quantum program, and send it and get it produced on a real quantum computer and on a simulation. So that's taken exactly 9 minutes. Thank you.